Okay, hello, Avery, Samantha, Addie, Will.
Hi, how are you?
Good, how you doing?
Doing good.
Awesome. So how about we'll just start first come, first serve. So it looks like Sam, you were in here first. So what can I do to help you today?
I was just really struggling with the LN rule.
Okay. Is there a practice problem you want to look at in particular?
Yeah, so it's number 3 on page 157.
Okay. Okay, so the goal on all the problems on this page are to take a derivative, and this one involves the ln, and so the ln rule is that when you take the derivative, you have some stuff in parentheses. Ln's always an operation on some numbers, like ln of 10 takes a number and squashes it down, and in this case the number is actually an expression, but it operates on this expression. So what we're going to do is take that and copy it right down here in the denominator. And then the ln rule says you look at that and put its derivative in the numerator. So another way, when I've taught this in the past, is say like the ln rule, if y is ln of some stuff, then the derivative of that is the derivative of the stuff. So like stuff prime over stuff.
Okay.
And so that's the rule that we're going to apply here. So we just write what the stuff is, and then we have to ask ourselves, what is the derivative of this? And now we get to go use a couple other rules. We're first going to use the derivative rule. So it's going to be the derivative of something minus the derivative of something. In the first part, we need to know what the derivative of e to the x is. And so there's a rule over here. Another rule we can add. So these are differentiation rules. If y is e to the power, then y prime is the derivative of the power times e to the power. So again, it's like, where did these things come from? These things came from mathematicians who used the limit definition and then saw patterns and came up with these rules. And so if your function fits e raised to anything in the power there, you're going to copy that, e to the power, and then write its derivative, multiply it by the derivative, either in the front or the back, it doesn't matter. Order of multiplication doesn't matter. So e to the x does fit that. And so I have e to the x, so I'm going to rewrite e to the x. And then I need to multiply that times the derivative of x, which is just 1. So there's really an invisible 1 sitting there. Okay, now the second half, what goes here is the derivative of e to the minus x. So that also fits the e to the power rule. So the rule says just copy it first. So that'll be e to the minus x. And then take the derivative of minus x. That's just a minus 1. So we'll have the minus there. And so if we were simplifying, it's e to the x plus e to the minus x over e to the x minus e to the minus x. That is a function that when you input an x, it spits out, you plug in the value for x, and it'll spit out how steep you are on the graph exactly at that point. So if I was interested in what is the derivative at 0, I would plug in 0 for x. I get e to the 0 plus e to the 0 over e to the 0 minus e to the 0. All right, so you just plug in the value, that works.
All right, thank you.
Okay, how about Will? How about you next?
Hang on, let me find it. It
Sure.
was from last week's homework, or I mean the homework that was due last night.
Okay.
Can we go over page 151 Can we do question 2?
Sure. Okay, so this one, Will's asking about, we're trying to solve for x, and the equation that we're given is ln x squared minus 2x equals 4. Okay, so when we have an equation, this one happens to be, just to use vocabulary, this is a logarithmic equation. It's got the equal sign, makes it the equation, and then it's got the log, so we have a logarithmic equation. All that means, though, is if we recognize that what we're going to have to do to solve it is to undo the log step right here, because right now we want to know when we're all done, some algebra later, x is like some number, right? That's what we hope to get to. But we're going to have to do some steps to get there. And right now, x is stuck inside this operation that Samantha actually asked us about earlier, this ln operation. Well, to undo a log, you have to apply the inverse operation, which is the e, because e's and ln's right next to each other, they cancel each other out. So those are from the videos. I didn't have time to talk about them last Wednesday, but in the videos from the asynchronous lectures, e's and ln's are just like other inverse operations. You know addition and subtraction, like addition increments things, subtraction decrements them. Multiplication and division, squaring and square rooting. So this is just another case of a pair of operations that are inverses. And this is the one, though, that's a little more confusing for students because what do e's do, what do ln's, they just seem much more vague. But e, when you take e of a number, it expands it, it blows it up. If you take ln of a number, like ln of 100, it squashes that number down and gives you a much smaller number. So e's blow things up, ln's squash them down. And there's the inverse relationship there. Okay, all that long-winded way to say the next step then is to undo this ln. You say, what's the inverse operation? That's exponentiation. But just like any other equation, whatever I do to one side, I have to do to the other. E and ln right next to each other, they're inverse operations, just like adding 5 and subtracting 5. Just get, you sort of cancel each other out, right? And so the next line we can actually write as x squared minus 2x equals e to the 4. Well, e to the 4 is just some decimal. I'm going to use my, I won't share the screen, but I'm just going to Google what that decimal is. So e raised to the 4, I can just literally ask Google equals e caret 4, and it's 54.59. Let's just say 54.59. So we have x squared minus 2x equals 54.59. Okay, well now at this point, it's getting a little better. It's now a quadratic equation. X squared minus 2x minus 54.59 equals 0. But this is probably where you got to, Will, where, okay, what do I do now? Because normally with something that's quadratic, you try to say, okay, well, maybe I can factor it into 2 linear terms, an x and an x, but how am I going to factor this decimal? Like, that factoring only works when you have nice integers. We don't. So what's a way to solve this equation? Anybody?
Quadratic formula.
Nice, quadratic formula. So ax squared plus bx plus c equals 0 has this formula that you probably remember. So you can just use the quadratic formula to solve this. And that formula, you have to figure out what your a, b, and c are. So there's really an invisible 1 sitting here, and that's going to be your a. This minus 2 is going to be your b, and then this decimal is going to be your c. And then you have to remember what the quadratic formula is, or look it up, or review it, but I think that was from our pre-test too. We did that in the orientation videos. So x is going to be negative b plus or minus the square root of, anybody remember? B squared minus
B
4AC.
squared minus 4AC.
Nice. Okay, so, you plug those in. That's just some calculator work. You can go ahead, but there's the setup. Just cranking away on a calculator, and you should get at most 2 values, because you could have 2 roots. It's a second degree polynomial, so at most you could have 2 roots. Sometimes you can have a repeated root. Probably not going to happen for this one. You're probably going to get 2 different values. Oh yeah, and so then actually, I guess we do have a way to check. It looks like our decimal at the bottom, if the answer is correct, is one of those is minus 6.45, and the other one's positive 8.45. Now, how could you check that those are actually correct? Like I'm looking at the bottom of the page. If I wanted to check if 8.45 is a solution, I would actually go back to the original equation, which was this. I've since changed it. It was ln x squared minus 2x equals 4. And we're saying x equals 8.45 is a solution. Well, you should be able to do ln of 8.45 squared minus 2 times 8.45. Take some calculator that, take the ln of that on the calculator, and that should be 4, right? That's a way to check it. Okay, good choice on that one, Will. That was a good practice one. How about Avery? Haven't heard from you yet.
I actually had the same question, so you covered it.
Okay.
Question on that page.
Okay, Addie?
Number 5 on 151, if we could
Good
just.
one. That's a really good one to practice. Okay, so Adelaide, do you like Addie or Adelaide?
Addie's fine.
Which one? Addie's fine?
Yeah.
Okay. All right, so Addie's question, we want to look at this, and one of the first things that's a little bit intimidating about this one is we've got this fraction, and maybe on this side it might be better to actually, it might help us out if we remind ourselves that's really a fraction too, 5 over indivisible 1. And the reason I say that is because then we can use a trick from the pretest, which was that you can cross multiply these things. So when I do the cross multiplication, the equation becomes 100 on the right-hand side, and then 5 times 2 plus e to the 3x over here.
Okay.
And now the equation looks a little bit better, but it's still an exponential equation, so this is still a new skill for us. But at this point, okay, well, x is stuck inside this parentheses, stuck inside an e, and we've got this 5. Well, the first thing we can do is get rid of this 5. It's multiplying by this, but if you want to get rid of it, you apply the inverse operation, which is division, but whatever you do to one side, you do to the other. So you would get down to this line, 2 plus e to the 3x equals 20. Still, okay, that's getting a little bit better, but again, we still have this e, so it's hard to just look at it and say, oh, x is minus 1, right? So the next step is to undo this 2. Well, this is adding 2, so if I want to get rid of it, I subtract 2, but whatever I do to one side, I do the other, or you can think about it as coming across the equal sign, changes the sign, however you learned it, but you probably get down to this step. E to the 3x equals 18.
Yeah.
Good, okay, and then this is the last piece, and this is the new part. All that was sort of massaging an equation with techniques, maybe from high school you hadn't seen in a while, cross multiplication, distributing, shifting something over. But now we have to deal with this, which is an exponential equation, because it's the equal sign and we've got an e, so it makes an exponential equation. I need to undo the e so I can get at this 3 times x. I can handle the 3x, but I need to get rid of the e. The inverse operation of e is lnning, but whatever I do to one side, I have to do the other. So really, I'm going to get down to like this one. Sticking ln, and I need that ln and e right next to each other. So that's why it was important to do all that work first. Okay, but whatever I do to one side, I do the other. And ln and e, it's like they go away, they're inverse operations, they cancel each other out. So the next line over here would be 3x equals ln of 18. Well, that looks a little scary until you realize ln of 18 is just a number in your calculator. So I'm going to go ahead and use my Google calculator here while you guys can do that as well. And I'm just going to say equals ln parentheses 18. And it's 2.89. We'll just carry a couple decimals there. And so again, notice what ln did. It took a number 18 and it squashed it down. Again, that's what ln's do. So 3x equals 2.89. And now, no problem, I can solve for x. This is just a linear equation, back to stuff from maybe in elementary school for some of you, dividing both sides by 3. So x is whatever that decimal, let's see, it looks like I'm saying this was like 0.9635. That seems about right, because it should be a little less than 1, right, from something that's almost 3 divided by 3.
I had another one. I don't know if anybody else wanted to go ahead. I was gonna look for it.
Go ahead.
I have another one.
Okay, how about Will, you jump in if you got yours ready, and then we'll come back to
Yeah,
that.
I've got mine ready.
Alright.
So it's intervals of increasing and decreasing on 137.
Okay,
Question 2.
all right.
Wow, great minds think alike. That's my question.
Okay, good. Okay, this is a good one to practice. I think I also got email from a couple people that my answer at the bottom is a little off. So maybe you guys don't have a question. It's just my answer that you're.
Oh, okay. Yeah, that's what I wasn't sure about.
Yeah, I thought I did it right too. I was a little lost.
Cool. Okay, well, here's the answer, and then if anybody wants us to work it, we can go through it. But here's what should be the correct answer, and it will be in future editions. That's why you guys are so helpful. Not to make you all guinea pigs, but it is a bit of a goal for you because you can help me find the errors. So next semester, students will see this as the answer on page 137, number 2. The answer should say that it is increasing from -2 to 4, and then decreasing when, let's see, x is less than -2 and when x is greater than 4. Okay, so Addie and Will, is that what you had?
I had closer to that,
Okay.
but I still did something a little wrong. I don't know what it was.
Okay, so let's go through it then.
Yeah, I didn't get the 4.
Okay.
Yeah, I didn't either.
Okay, let's go through this and make sure we got this right. Okay, so the function, and are you guys able to see this? That light,
Yeah.
so, is it better with the light?
That's a little bit better.
A little
Yeah.
better?
Yeah.
I know it's just gonna have that, I won't write over
Yep.
there. We'll leave that off limits for now. Okay, so the function is minus x to the 5th plus 2.5 x to the 4th. Plus 13 1/3 x to the 3rd plus 5. So if you're a guide, this is something to start making a little sheet of notes that you're going to study for the final. And my clue for me, the visual picture I have when I'm trying to do intervals of increase and decrease is to think about the f prime line. So I want to do something like this. Remind myself it's f prime. I'm going to put some CPs on there, however many I have. Maybe there's 3, CP1, CP2, CP3. That would, if there were 3, it would divide it into 4 intervals. I pick any point from each interval. So I'd pick 4 test points, plug them into the derivative. If that derivative is positive, that means that the slope is positive. So the function has to be increasing. And so I'm just going to pick a point. Like that's my study guide right there. Or maybe even just, putting in a sample of what might happen. So if it went like this, we'd be increasing a little more, decreasing, and then increasing again. So we have to do that for ours, which the first step to get CP is the definition of the CP. What makes it so critical is that it's a possible max or min. It's a possible place where I might change from increasing to decreasing or vice versa. It's a place where I have a horizontal tangent line. So all that helps me remember that I need to take a derivative and set it to 0. Okay, some nice power functions, no problem. We don't have to do the ones that were as difficult as Sam started us off with. We don't need to use more complicated rules, right? This is really the heart of business calculus. You have to be able to do these polynomials like that and by hand. And hopefully after you've finished chapter 2, these are the ones that you welcome, like you look forward to seeing one of these on the test. Okay, so minus 5x to the 4th will be the first term. Plus, let's see, 2.5 times 4 is what, 10?
10.
Yeah.
10x to the 3rd. Let's see, maybe I should write that as a fraction. That's what, 40 thirds? 13 and a third is 40 thirds. Or if you don't like the fractions, turn them into decimals. Like if, again, I find that every semester that really helps a lot of people. So if any of you are worried about what I just did there, just, 13.3333. And then you multiply that by 3, so we're just going to get plus 40x squared plus 0. Okay, questions on that derivative? Good, okay.
Good.
Okay, so then the next step would be, okay, I need to find values of x that make this a true statement. Maybe you can guess one right off. Can anybody guess a value that's going to work? What if x equals 0? 0 equals 0 equals 0, 0. Right, so we should get a CP of 0, and that's actually what's going to be nice to help us when we factor, because the next step might be, well, I actually see that there's like factors of 5 in each term, so I'm going to pull out a 5, and I'm going to pull out an x squared, and then I'm going to see what I have left. And when I do that, I'll have something plus something plus something, just to give the structure, just to remind myself what I want to do. So in the first term, the only thing that's left is a minus sign and an x squared. In the second term, what's left is a 2 and an x. And in the third term, what's left is an 8. Okay, so that's where, like, remember, you can set each factor to 0. Well, already I know 5x squared equals 0 solves x equals 0. So we know there's that CP that we might have seen here. So we know we're going to have one CP that we can put on the list. But this next term, we want to also factor, right? It's a quadratic, and we want to see if we can turn it into 2 linear factors. So we have 5x squared, and let's see, then we need to take this to a minus x and an x, a 4 and a 2, and now we just have to work on our signs to see if we can get this to work, to give us a positive 2. So it looks like maybe I need a minus and a plus, no, a minus and a minus, a minus and a minus maybe. All right, let's see if that works. Negative x squared. No, that doesn't do it, does it? This minus sign really throws me off here. I always factor when they're positives. Do we need plus plus? Does that do it? So then maybe 4, 2. I think that does it. Help me check that out for me. Minus x squared.
And that fell off. Yes.
Yeah.
I think that factors does give us that. Checked it a couple times. So now we have this quadratic, but it's easy to see that x equals 0 is a CP. Then we have this linear term, and it's easy to see that x equals 4 solves that. And then lastly, x equals -2. So we get 3 CPs. 0, 4, and -2. And then remember, we put them on an F prime line. It's a number line, so you put them in order. So I write them over here. And this, again, this is important because sometimes students do a great job here, but it's a number line, right? So -2 comes first, then 0, and then 4. Okay, now we see that there are 4 intervals, and we see where I had the answer up there before. We see where that like 2 and 4 came from.
And then you used x equals 0 because it's set to equal to 0 at first.
Yes, because you had said that first one, 5x squared equals 0. Again, if you want to just go through the division, like x squared equals 0, and take the square root of both sides, x is 0. So if I keep
Sure.
playing yours.
Is there always going to be a 0?
No, not always. That's a good question, Will. It would have to have like some factors of x in front, like x by itself or x squared or x cubed. That's the only way you'd get a 0 as a CP.
Okay.
That's a good point, Will. Okay, now that we have these and we're sure, what's another way that you might check that this was true? Pull out your calculator and graph the original function. And maybe I'll do a screen share real quick with, what do we like, Desmos? Let's go to Desmos. All right, so we were at Google, but let's change this to Desmos. Calculator, sure. The original function is minus x up to the 5th plus 2.5 x to the 4th plus, let's just write this one as a decimal, 3x to the 3rd plus 5. Okay, and then I think I should zoom out a bit to see all the terms here. Oh, whoa, that's crazy. So maybe that's not useful for us to take a look. That's crazy. Well, we do see some of the CPs, like, so I'm gonna see if I can zoom up. Like this one, when I zoomed in, actually isn't so pointy. It would look a little more curved, but that was the one at -2 right here. And then there's the one at 0 where it snakes through. And if I zoomed in, it will look flat right there for a moment. And then this other one must be just way up here. But that's the one at 4. Must have another peak. Gosh, I don't even know how far I gotta go. But at any rate, that's where that other guy is. Oh, I guess because 4 to the 5th is so big, or 4 to the 4th. Oh, I guess this 4 to the 4th is what, 16 times 16. That is big. And then times 2.5 plus. Okay, so that could be a huge number there. Okay, so we'll stop the share. Back to the whiteboard. And so that was just to visually check your CPs. Like if you weren't confident, maybe again, Will was asking a question about this and he might have forgotten the CP. If you do forget a CP, that's going to totally change, what you've done here. So it's nice to have a visual and go back and look for those visually. That's why we spent so much time in chapter 1 building up that intuition. Okay, now that we've got these and we've checked them, the next thing we want to do is pick a point from each interval and plug it into the derivative. It might be really nice to actually plug into this form of the derivative right here in this box.
Oh.
And so if I try like -3, f prime of -3 right here, what I'm interested in is the sign. And what I see is it doesn't matter what I plug in, and I square a number, multiply by 5, that's got to be positive. So this first term is always positive no matter what I plug in. But the second term, when I plug in -3 and then take the minus of that and add 4, that's going to be a plus. And then the next term, -3 plus 2, will give me a minus. So plus times minus is a minus. So it has to be decreasing from -infinity all the way up to -2. All right, now the next one, I can pick something between -2 and 0, so let's try -1, f prime of -1. When I plug -1 in, again, I still just get a positive here, because squaring that's going to be positive. And then -1 minus that, so that's +1 plus 4 is positive. -1 plus 2 is positive. So positive times positive times positive is positive. Therefore, it is increasing so far from -2 to 0, but I think what we ultimately are going to determine, it goes all the way over to 4. Oh, that's right. That's because that CP went like that in the middle at 0. It was like increasing, then increase some more. So I pick something over here. It doesn't matter what you pick, but you know, it makes a lot of sense to try like 1. That's easy to plug in rather than like 2.75, right? So make the arithmetic easy for yourself. And again, you can plug in here, no problem, but I just think it was easier for us here. So when I plug in 1 to the derivative, I get a positive times a positive times a positive. Yeah, so there was our other conclusion. And then we know from the picture and from our answer that this last one has to be minus, but let's go ahead and check that. F prime of 5. So again, 5 times 5 times 5 is a positive number. -5 plus 4 is a minus, and 5 plus 2 is a positive. So positive times positive is minus. And that picture right there has everything you need to do, everything you need to know. You just have to write it down, that it was decreasing, then increasing from 2 to 4, and then decreasing from 4 to infinity. And then just a little bonus or preview of some stuff we'll see in the next chapter is you guys now kind of know the shape of this. Like it went decreasing, increasing, increased some more, and then decreased. And once you kind of see that, it was, of course, way stretched out for us. Remember, it was like really tall, but it had that basic shape. And what you can see is when you go from decreasing to increasing, this has to be a minimum. And we're going to call that a local minimum this week. And then this, it is going to be something that we'll learn in chapter 3. It's going to be something called an inflection point. We'll get there. But the last one is also kind of common sense, is this one we went from increasing to decreasing. This one has to be a local max.
I see what I did there. Thank you.
Thank you.
Mhm.
Also, one more question. Just nothing about math. Just about like the homeworks.
Sure.
So since we like the answers are there, are you grading it for like accuracy, or is it just like completion?
Yeah, we want to see your work. So I've got a grader help me. There's just so many of you, and
Right. No, I
I'll check
understand.
another one. So the grader's name is Chloe, and she and I will tag team, but mostly it'll probably be her. And we're just looking to see your work. And we're using this, you don't have to try to get perfect on every page. Like the idea is that you'll be ready to do the challenge problem and then you'll be ready for the final. So this
Right.
is all just like, you know, again, don't like stress out that I have to get everyone 100%. You do have the answers. And again, we're looking for thought and seeing the steps. So we want to see that you know how to take the derivatives. We want to see that you know to do the F prime line. We don't want you to just throw it into Wolfram Alpha. You can check your work, that's great, because Wolfram will sometimes show steps, and that's helpful. But we want to see thought process. And several of them, that's also why on most of the homework pages, the calculation ones that have the lines, I often give you choices. Like you don't have to do every single one on the page. I just want to know that you feel that you can do them. Like you know the process for that type of problem. Then move on. You know, I don't need you to do 100 of them. I only need you to do a few on each page.
Okay. Right. Thank you.
Mm-hmm.
I just have one more question for the exponential rule.
Yeah.
Number 4 on 155.
Okay. All right, so Samantha's got another great question for us because we get to go over a couple properties and a couple rules. So this one, we don't have yet a, in our list of differentiation rules, one that involves a fraction. And in fact, I told you that this semester we don't have to do the quotient rule because that's the rule that looks like a fraction. In fact, I'll just go ahead and put it down here. Don't copy this because you don't need to know it, but I just want to show you the form of it. And we'll use that, and we'll talk about how we are avoiding that rule. Okay, so the rule is if your function has a numerator and denominator, which the one Samantha picked does, then you could use the quotient rule because it is a quotient of two things. And the derivative would be written this way: denominator turns to the numerator, minus numerator turns to the denominator, all denominator squared. And again, we're not going to go through that rule. There's ways to avoid it. You know, there's some cases in which you would have to use it, but again, not so much for business calculus. So we don't have time this semester to do it in this crazy COVID semester. So there has to be a way that you can still do this one with the rules that you need to know this semester. And so this is going back to the pretest, Samantha. So we can do this by remembering rules of exponents, because this is really just a base. E is 2.718, but it's got something in the exponent. So it's a base with some variable exponent. And this is the exact same thing as e to the x squared, e to the minus 3x, because this can cross the bar. And so sometimes we go the other way, but this time we're going to cross the bar and go up. And now they have the same base. And so this is, again, rules of exponents, probably from a high school class, things you haven't seen in a while. That is the same thing. So that is our function. So we can actually say f of x. I could have started here and it would have been a much easier problem for you, right? If I'd said for number 4, if I was just like, hey, differentiate this. But I wanted us to just learn this property that, hey, those rules that you learned way back, and it's like, why am I learning these? Well, here's a use, because it saves us from having to do that rule. And then again, why am I taking derivatives? Well, think about slopes of tangent lines, think about the challenge problems. There's some really cool challenge problems where those derivatives help you find an actual, like, solve a murder mystery, find a detective stories. So solve these different cases. That things that actually do happen, like in court. So, but for us, we just want to, now that we're at this point, take the derivative. Now it is one of the rules you need to know. It's this one here, the e to the power rule. And so the derivative is, rewrite the thing, e to the x squared minus 3x, and then multiply it. It doesn't matter where, in the front or the back. I'll just stick it in the front. The derivative of that power, and that's just a nice polynomial function. So the derivative is 2x minus 3. But this wasn't part of Sam's, or Samantha, I don't know which one you prefer.
Sam's good.
Yeah, okay. So Sam's didn't ask us this. We could stop here for Sam's question. This would get you, full credit on that particular problem. But what if I said find the CPs? So let's practice while I've got you guys here doing this, because this is something that can cause a little trouble for folks every semester. So definition of a CP is when your derivative is 0. We've already done the hard work of taking the derivative, and now we're trying to solve the equation in the box. And actually that looks pretty messy, but it's not so bad because it's already factored for us. There's really like 2 things being multiplied, right? That's helpful. And one of those things is a linear. So I can set 2x, like the whole point of factoring is you can set each factor to 0. So 2x minus 3 equals 0, and e to the x squared minus 3x equals 0. So I have 2 equations to solve. The first one's really easy to solve. X is 3/2. So like 1.5, that is a CP. We're sure of that. And then we have to solve this other one. This is an exponential equation. You guys had us work at least one of these already today. And so I apply the inverse operation, the ln, whatever I do to one side, I have to do the other. So I would get down to this line, x squared minus 3x equals ln of 0. But if you remember from the asynchronous videos that were posted, e to the anything equals 0 has no solution. Why is that? Because ln can never be 0. Think about the graph of ln. So if you tried to like put that in your calculator, you'd get this backwards error button, backwards error sign, right? That's an error because ln, the graph of that looks like this. It never touches 0. It gets really close to it, but there's actually an asymptote there. So there is nothing that you can do that's ever going to solve this. There is no value of x that's ever going to make that a true statement. And that's true e to the anything. I think I wrote it like this in one of the videos. E to the anything up there, it looks like a little bat or something, but it's anything. That has no solution. So it's actually kind of nice to look at this here. Don't get so worried because this whole back half goes away and you just get one CP. That's possible, but let's actually think back to our original function. Like let's visualize that CP. So let's go to Desmos again and take a look at what that function looks like to find the CP visually. So let's get rid of that one and write y equals something in parentheses divided by something. So we're going to put the, as it was originally given, e up to the x up to the squared, and then e up to the 3x. Oh, this is another one. We're zoomed. It's going to be hard to tell again. Oh, there he is down there. That little point way down there, which we're saying is 1/2. So maybe let's see if I can zoom in enough. Oh, I'm going the wrong way. Zoom in. Yeah, there it is. Okay, it's getting flatter. Otherwise, it just is a U and then rises up sharply, and that makes sense because again, E like explodes numbers. And so it looks like it's flat right around there, and that is in fact 1.5. So good to check. All right, great question. Again, Sam, you're giving us ones that really get to practice a lot of different techniques. Okay, Connor, how about, haven't heard from you yet. Do you have any questions? Anything you want us to look at?
I just got here. I don't know if anyone already asked this, but I had some trouble with the questions on intervals of increase and decrease.
Yes, so Connor, we just did that one, but we can work another one maybe. Let me pull one from the back of the chapter. So we just did one, and you can watch the video because I'm going to post this. We just did on page 137, number 2. So you get to watch that on the video, but let me pick another one for us because those are good ones to practice. I can promise you that this will be on your final exam question exactly like this. Find the intervals of increase and decrease for this, and the only thing that changes is the f of x function that I gave you. Okay, so I'm gonna pick something from the end of the chapter. Okay, let's pick one. This is on page 199. How about number E? 5E. Okay, so Connor wants us to practice it in intervals of increase and decrease. This is good because we get to practice a couple things again. Remember the picture, put that back over here. Whenever they ask you about intervals of increase and decrease, I think visually that I just need to make an F prime line. I labeled an F prime line, so I remind myself to plug into the derivative and not the original function. I put however many CPs I have on there. That will divide it into, and this, if there was 3 CPs, it would divide it into 4 intervals. I'll pick something from each interval. As long as the point lies in the interval, I plug it into the derivative, and I'm just looking at like the sign pattern. I might have something like that. We'll see what we get for this particular example. But if it turned out like this, I would say it is increasing from minus infinity up to that first CP, maybe that was 7. And then it's increasing again, maybe this last CP is 20, so it goes from 20 to infinity. Okay, so if that's the visual picture that jogs your memory, this is what we're trying to do. We can do all this without even knowing what this function looks like. But if you're a visual person, you might want to just start with the picture of what it looks like. Go to your calculator, enter this function, so you kind of have an idea, and this will help guide your calculations. Not necessary though, because again, the calculus tells us, I don't even care what that looks like. I can do all this analysis. And the analysis starts by taking a derivative and setting it to 0. Why are we doing that? Because that is the definition of a CP. So that'll give us the things to fill in here. Easy derivatives, again, we'll have 4 times 3/4 is going to be a minus 3x cubed plus 3 times a third. So then we just get x squared plus 0. All right, so now I need to find values of x that make this equation, what's in the box, true. You might be able to guess just by looking at this that one of the CPs is x equals 0, or it's okay, you don't need to know that. You don't need to like sit here and fidget and guess. You can just factor it. Okay, so I see that there's some stuff before a plus sign and some stuff after a plus sign. And what I'm gonna do is factor out anything that's common. So I'm gonna take out an x squared. I see that there's that in each piece. And then what I'm left with, again, is that same structure. There's some stuff before a plus sign, some stuff after the plus sign. What's left before the plus sign is a minus 3 and an x. All those together. You can always check by multiplying it back in the other direction. Yeah, I get minus 3x cubed to make sure you've done the factoring. The only thing left after the plus sign is a 1. Took everything out there. And this is what sometimes students forget to put, but you have to have that because when you do the multiplication back and distributing in the other direction, just to check that you've done it right, you need that 1 there. Okay, and now I have 2 factors multiplied together equals 0. The only way 2 numbers can multiply to 0 is if at least one of them is 0. That's the special rule of 0. And so we will see that x squared equals 0 and minus 3x plus 1 equals 0. First one's easy. X equals 0 is the CP. That's the only thing that'll solve that. Second one's also easy. That's just a linear equation. And so what x is positive 1/3. So we see in this case, we got 2 CPs. We didn't actually need this many. So it makes our f prime line a little bit easier. And we put them in order because those are numbers on a number line. And so 0 comes before 1/3. So we make sure we write them in that order. That's a key piece. Otherwise you'll get, the results will be mixed up. Okay, so then that divides our number line into 1, 2, 3 intervals. I pick a point from each interval, plug it into the derivative, not the original function. I'm not interested in heights right now. I'm interested in rates. Is my slope positive, so then I'm increasing, or is my slope negative, so then I'm decreasing? All right, so I'm gonna pick something like -1 over here, f prime of -1. So I'm gonna plug into my derivative. It doesn't matter, you could do it at this line or at this line. I think it's easier when you plug in to the factored part. So this is f prime of x. We want to know what f prime of -1 is. So that's -1 squared. Doesn't matter, it's positive. And then -1 times -3 is +3 plus 1 is positive. A positive times a positive is a positive. So that first interval from -infinity up to 0 gets a positive sign because it is increasing. And that's what that actually means. That plus sign means your slope of the tangent line is positive, therefore you're increasing. Again, and when you're writing that little plus sign, you're really saying it's increasing. All right, we're going to do the same thing, but now we're going to plug in something. Okay, this is going to require either decimals if you don't like to see the fractions. So I need something between 0 and 0.333. We maybe try 0.1 or 1/10, however you like to think about it. So f prime of 1/10, let's say. Doesn't matter what you pick, you just want to pick something that's going to make the arithmetic easy here. So 1/10 squared, 1/10 times 1/10, that's 1/100. It doesn't really matter, it's just positive, right? A positive times a positive is positive. So that's positive there. And then -3 times 1/10, that's -3/10 plus 1. So that's going to be positive. Positive times positive, positive. So the next interval is also increasing. And one more thing to check, the last interval from 1/3 all the way up to infinity. So I can try something like +1 here. So when I plug +1 into the derivative, I get a positive and a negative. And those two multiply together to give me a negative. So therefore I must be decreasing. And then once you have that f prime line, that's all the information you need. It's just a matter of writing it, actually writing it out on our test for us, that you know that how to interpret that it means the function f is increasing from, let's see, -infinity all the way up to 1/3, and f is decreasing from, let's see, x bigger than 1/3. That'll do it. You can write it that way, or sometimes the answers at the bottom of the page I wrote in interval notation. Means the same thing. And then you could always check your work. So let's see if Desmos gives us a better picture for that original function. So let's check this one out. One more screen share. And let's change to this polynomial, minus 0.75 x up to the 4th plus 0.33333, just because I don't feel like doing the fraction, x cubed plus 0.25. Okay, so then let's zoom out to make sure we've got all the terms that we need. And we found that there were a couple CPs at 0 and 1/3, so we're going to need to move in to see if there's any little slight changes here. So level right there at 0, and then it's really hard to see. Let's see if we keep zooming in, if we can see a little slight change. Oh yeah, there's a slight little, that's such a little sneaky function, right? So it's flat right there. CP right there, that is a horizontal tangent line. And then it's just the slightest little rise up, and then it changes again. So increasing from -infinity all the way through 0, and then it's just the slightest little uptick again, still increasing, and then it's not till right about here that we start decreasing. And that is, oh yeah, that is 0.33. So cool. But had I been zoomed out, like that's what I was like, wait a minute, kind of looks flat. Still looks flat there. It's hard to see that little second CP, but that's what's so neat about that problem, right? That's actually a pretty cool one to work, because you see where the visualization could be deceiving, but the calculus, you're not going to miss that. Like we had to just know that we knew from the calculus it was there, and then we kept zooming in. So cool example. Thanks, Connor.
So just for the decreasing part, so we would say that 1/3, it starts at 1/3 and then it decreases all the way to positive infinity.
Yep, that's a good question. So you could have written it like this, Will. You could have said 1/3 less than x less than infinity. You could have written it in interval notation from like 1/3 up to infinity. Or you could just say it just like you did verbally. Write it all out in words.
Awesome, thank you.
Thank you.
I'm good. I don't have any more questions.
Yeah, I
Thank
don't
you very
have
much.
either.
All right, yeah, sign off or stay on. If you got more, stay on. Otherwise, thanks for calling the meeting, Will. Thanks for suggesting it.
Thank you.
Yeah,
Thank
thanks,
you.
Will.
Appreciate
See you
it.
on Wednesday.
Yeah, we'll see you Wednesday. Oh, how are the challenge problems going?
We haven't, me and my group are talking about, I think we're gonna meet on Tuesday sometime.
Yeah, my group met today and we got a little stumped, but we know what we need to do and we're gonna meet tomorrow to like,
All right,
finish the other half. Yeah.
Awesome.
Okay,
Thank you.
thank you.
Bye,
Bye.
everyone. Have a good night.
You too.
Good night.
I think I just had one more question.
Okay,
Like
Con-
about when you're trying to find whether or not it's increasing, you're just trying to see if it's like positive when you plug in like the values.
exactly.
negative.
That's all. So that's a great summary, Connor. When you plug in a number to the derivative and it's positive, what that means is that it's really saying the derivative is the slope of a tangent line. If the slope of the tangent line is positive, you'd be pedaling uphill. It'd be increasing.
Okay. Okay, thank you.
That's it?
Yeah.
Okay. All right. Well, have a good night.
You too.